Hello, AP Chemistry. How are we doing today? Hopefully y'all are doing well. So today we are going to be continuing our Unit 7 notes on equilibrium. And for that, you do need to make sure you've got a calculator. All right. Now, today's lesson is going to be over something called Rice tables. And that is going to fall in 7.7 and 7.8 on the AP calendar. So this is going to be what you can use to do some extra practice on this unit. So what is a Rice table? Well, when we're solving an equilibrium problem, it's important to follow a series of steps. Because when you skip a step, that can lead to issues with your problem. That can lead to you getting the wrong answer, and which that ultimately results into lower points on your tests and at the end of the year, the AP exam. So Rice tables help us to organize everything to make sure that we do not skip anything. All right. So let's take a look at our steps for solving equilibrium problems. The very first step that we should do is write a balanced equation. Okay. That should be the absolute first thing that you do. Once you've done that, you need to set up an equilibrium expression, which you've already learned that. You learned that the past two classes we've been working on setting up equilibrium expressions. Last class, we know that we actually focused on reaction quotients instead. Okay. Third step is if you cannot tell which direction the reaction will go, be it favoring the reactant or favoring the products, then you're going to have to solve for Q. Okay. After you've done that, then you can set up a chart that's going to include your equation, so that balanced equation that you wrote, the initial concentrations, the changes in concentration in terms of X, and then the final concentrations that we get. Once we've got that, then we're going to substitute these final concentrations into our equilibrium expression and solve for that X. Okay? Then we're going to check our answer and make sure it's logical. Now, here is something kind of a shortcut or a note for you, is that when we're solving an equilibrium problem, sometimes our negative or positive X's are actually treated as negligible. And basically all it is that when we're comparing those X's to the value that they are being removed or added to, if that number is less than 5%, then we can assume it's negligible, which basically just means that they're going to have such a small effect on the overall that we can just assume that they don't affect it. Okay? And so if there is not a negligible, then we're going to have to either solve it normally, or we might end up having to use the quadratic equation. Now, something that I'll note is that the quadratic equation is not actually going to be tested on the AP exam, but in this class, I'm actually going to give y'all a challenge problem that uses the quadratic equation. So you might need to pull some of that out of your memory a little bit. All right. Now, one of the things that always confused me a little bit was when I'm trying to figure out if something is negligible, how do I recognize if it is 5%, less than 5% of that number? Well, there's a simple way, and it's called the rule of 100. So the rule of 100 states that if the concentration of that number divided by K is greater than 100, we can assume that it's negligible. So basically, you can take that concentration, divide it by your K value, and if it's greater than 100, we can assume that it's negligible. All right? Another way that I've been taught to recognize if something is negligible, and this is kind of a generalization, okay? So it does do a lot of generalization here, is that if my value is 0.001, and then we got a K there, to 1,000. So if we're less than that 0.001, or if we're greater than that 1,000, then we can assume that it is negligible. Okay? All right. So let's actually solve a problem using this kind of general idea. So it says at 700 Kelvin, carbon monoxide reacts with water to form carbon dioxide and hydrogen. And we've got our balanced reaction there. So CO plus H2O in a reversible reaction produces CO2 and H2. And they tell us the equilibrium constant for this reaction at 700 Kelvin is 5.10. Consider an experiment in which 1 mole of CO, 1 mole of H2O are mixed together in 1 liter flasks to calculate, or at 700 Kelvin. Calculate the concentrations of all species at equilibrium. So the very first thing in a Rice table is the reaction. So R stands for reaction. And so that would be your balanced equation. So I have CO plus H2O in a reversible reaction produces CO2 plus H2. Okay? The next thing is going to be the initial. So this is the initial concentration. So for CO, we were told that the initial amount of moles I have is 1 mole. And we were also told that they were mixed together in a 1 liter flask. So our moles per liter is 1 mole divided by 1 liter, which is 1 molarity. So I found that my initial concentration for carbon monoxide is 1. Then I do the same thing with H2O. I found its concentration was also 1. Now, right here, I've got my products. The initial concentration of my products is 0. Why? Because we haven't made any products yet. So the initial is 0. Okay? Now let's think about how they're going to change. Well, the change is, thinking about it, reactants are going to do what? They're going to be consumed as a part of that reaction, right? So the amount of reactant is going to decrease. The amount of product is going to increase. And so we would see a decrease in X here for the CO and the H2O, and we would see an increase in X for my CO2 and my H2O. Okay? Once I've got that, then I can come up with my final concentration, which would be that equilibrium, right? So it would be 1, that initial concentration, minus how much ever it changed for the CO. It would be the same for H2O. For CO2 and H2, all they would do would be increase by whatever that change is. So whatever X is. Okay? All right. So now I've got my Rice table set up. Another thing that I also needed to do was write my equilibrium expression. So my equilibrium expression here says Kc equals CO2, the concentration of CO2, times the concentration of H2, divided by the concentration of carbon monoxide, times the concentration of H2O. So products over reactants here. All right. And so when I plug in my numbers here, what I'm going to find is that I had a concentration for CO2 of X. For H2, it was X. So really that's X squared, right? Divided by my carbon monoxide, which was 1.00 minus X. And my H2O was the same, 1.00 minus X. Again, since those are the same, that's basically squared, right? So if I were to rewrite that, it would look like this. X squared divided by 1.00 minus X squared. And we know that that is going to equal my K value, 5.10. Okay? So how do I solve this? Well, looking at this, on my right side of the equation, everything is squared. So the easiest thing to do is go ahead and square this. What that's going to do is that's going to get rid of this, and that's going to get rid of that. Okay? So I'm actually going to rewrite this. So I've got 5.110 equals X squared over 1.00 minus X squared. We're going to square root this entire thing. And what I find, the square root of 5.10 was 2.26. That equals X over 1.00 minus X. Then I need to multiply both sides by the bottom here. So times 1.00 minus X. That's going to cancel that out. So then we times this side by 1.00 minus x. And we're going to get 2.26 minus 2.26x equals x. Then I'm going to add both sides. I'm going to add 2.26x. And I get 2.26 equals 3.26x. And then I'm going to divide both sides by 3.26. And I'll find that my x equals 0.693. Okay, so now I've got my x value. So now all I do is I take that value and I come back over here to my equilibrium expression, and I actually plug in, or my equilibrium, and I'll plug in those final concentrations that value. So the question asked me to solve for the concentrations of all species at equilibrium. So for carbon monoxide, it is 1.00 minus my x value, which was 0.693. So the concentration of carbon monoxide is 0.307. Okay? CO. I do the same thing with my H2O. 1.00 minus 0.693 equals 0.307 for H2O. And then I do the same thing for my CO2 and H2O. So for them, it's just 0.693, right? Because that's my x value. Sorry, H2, not H2O. These would be my answers there. And so that would be me solving through that entire problem, okay? Now, one thing I will note, I'm going to come back up here just a little bit, is that when we're looking at our change, the change should reflect a coefficient. So if I had a 2 in front of here, then my x value would also be a 2. It would be 2x, okay? So do keep that in mind. All right, so now let's solve this next example. So here it says, I've got carbon, which is a solid, plus carbon dioxide, which is a gas, in a reversible reaction produces 2 carbon monoxide, which is a gas. If the Kp for the following reaction is 2.4 times 10 to the negative 9, and the initial concentration of CO2 is 2 atmospheres, what are the partial pressures of the substances at equilibrium? So then they give us a hint to make the necessary assumptions to solve. So first thing that I like to do is set up my Rice table. So remember Rice, we've got our reaction, the initial, the change, and then where we would be at equilibrium, so that final. So my reaction was carbon, which was a solid, plus carbon dioxide, which was a gas, in a reversible reaction produces carbon monoxide, which was a gas, and there would be a 2 there at the front. Okay, now I need to fill in my Rice table. So first off, if carbon is a solid, do we take it into account for equilibrium? No, we don't. So we would basically just put a line through that and say that that has no effect. Okay? So now I can go ahead and solve the rest of this. So carbon dioxide, they told me my initial concentration of carbon dioxide, or my initial pressure, is 2 atmospheres. And my initial for carbon monoxide would be 0. Why would it be 0? It'd be 0 because the reaction hasn't occurred, so there's no product yet. Second, my change. Well, how's my change going to happen? Well, I know that my carbon dioxide is going to decrease where my carbon monoxide is going to increase. But something to note is that carbon monoxide is going to increase by that 2x. Why 2x? Because we've got a coefficient of 2. Okay? So now we can just fill in everything else. So what I found was that carbon dioxide, to reach equilibrium, would be 2 minus that x value, and carbon monoxide would increase by 2x. Okay? So next thing that we would do is we would write our equilibrium expression. So I know that Kp equals the pressure of CO squared divided by the pressure of CO2, but it is not squared. Okay, and then I'm going to go ahead and plug in my numbers. So my Kp was 2.4 times 10 to the negative 9, and that equals my CO, which we found to be 2x. We're going to take that and we're going to square it, divided by 2 minus x. Okay? Now, before we move on, we need to decide whether or not that x value here, this, is negligible. So is it negligible? Well, how do I know? Well, there's a couple different ways. First way to look is see, okay, if I've got 2.4 times 10 to the negative 9, is that value super small, which meaning 0.001, less than 0.001? Or is it super big, which is greater than 1,000? Well, it is very much less than 0.001, okay? So that's one way we could look at it and recognize that it's negligible. The other way is to follow the rule of 100, which basically would be us taking that concentration. So in the case of this, the concentration was 2. And we're going to divide that by our K value. So 2.4 times 10 to the negative 9. When I do that, what I get is 8.3 times 10 to the 8th power. Is that number greater than 100? Yes, by a lot. So that tells me that my K value is that X value is negligible. Okay, so we can assume that this is negligible. And so since we assume that's negligible, if I were to rewrite that out, I would get 2.4 times 10 to the negative 9 equals 4x squared divided by 2. All right? So now I can go ahead and keep solving. So 2.4 times 10 to the negative 9 equals 2x squared. Divide both sides by 2. And we're going to get 1.2 times 10 to the negative 9 gives me x squared. I'm going to square root both those sides, and I'm going to find that I have 3.5 times 10 to the negative 5 for my x value. Okay? Now, I need to solve for my actual question. So what are the partial pressures of the substances at equilibrium? Okay. Again, I'm just going to plug in my numbers here. So for CO2, it would be 2 minus that value, which would be 3.5 times 10 to the negative 5, which is going to give me basically 2, right? It's such a small thing that it didn't really affect it. So 2 atmospheres would be my pressure. And then for my carbon monoxide, it would be 2 times 3.5 times 10 to the negative 5, which is going to give me 7.0 times 10 to the negative 5 atmospheres of CO. And that would be that. So now what I want y'all to do is go ahead and solve this next problem here. And then, so pause your video, and then we will go over it. All right. All right, y'all. So this is what you should have ended up with. So for your rice table, there you can see it set up. So for my E, for that equilibrium, at the end, I should find that it was 4 minus x for A and B, and then 2x for C. Made my equilibrium expression here, which would be K equals concentration of C squared over a concentration of A times concentration of B. Plugged in my numbers here. Now, y'all, one thing that I do want you to note is that I actually solved this even though without assuming that x was negligible, even though it technically is. And I did this because I wanted y'all to see how much more work it is if you do not make that assumption, okay? And so looking through this, what you can see is that my values here start to get a lot harder to work with, and I end up with the exact same answer. So if I were to solve this by assuming that that x is negligible, then I would end up with 1.06 times 10 to the negative 3 as well, okay? And so I did want y'all to see that so that y'all could recognize, okay, well, I understand that I don't need to add x if it is negligible because the overall effect is going to be so small that it won't affect my answer, okay? All right, so I found that my x value equals 1.06 times 10 to the negative 3. I came back and I plugged that in. So I had 4 minus the 1.06 times 10 to the negative 3, which we know has such a small effect that we essentially keep it at 4, right? So I have 4 molarity for my A and B. And then C, I did 2 times that 1.06 times 10 to the negative 3. And I found that it equals 2.12 times 10 to the negative 3. All right? So that would be how you solve it. Now, this next problem that y'all have here is kind of set up in how you could see this on the AP exam. So this is actually an FRQ from the past. So what I want y'all to do is I want y'all to actually give a shot at completing A through E on this problem and seeing if you can solve for that equilibrium expression, all right? Or solve each of these things that it's asking for in this equilibrium problem. All right, so go through it. I'll actually have all the answers here in just a second, so I'm going to pause the video, or I want y'all to pause the video. I'm going to show all the answers here, but I'm just going to go through each of the answers, and then I'll see how y'all did after that. All right, y'all, so let's go over this. So for A, your equilibrium expression should have been K equals the concentration of H2 to the second power times the concentration of S2 divided by the concentration of H2S to the second power. And then for B, we used a rice table, and we found the following here. So filled in that initial change and the equilibrium there. Now to do that, to solve for that initial concentration, I did actually have to convert that grams over there that they gave me for the H2S into moles, and then I also had to divide that by the volume, which was 1.25. And so that's what gave me the concentration of the H2S. And then one thing that I recognize is that they actually told me in the problem that there was 3.72 times 10 to the negative 2 moles of S2 at equilibrium. And so since that's at equilibrium, I know that that's going to get me to that value of X at the end. And so I can take that that number of moles and I can divide it by my volume, and that will give me my molarity. And then that would solve for S2, which was an X value, right? And so then I can find that my X value equals that number. Now, once I've got that X value, then I can go ahead and plug it back in. And what I found was that H2 equaled 0.0596, and that H2S equaled 0.0202. Right, so that was part B. Part C then, I had to calculate the value of the equilibrium constant. And so again, I have my Kc expression, I plug in my numbers, and I got my Kc to equal 0.259 right here. All right, now let's take a look at D here. So for D, we would use PV equals nRT, rearrange that equation, and I found that my pressure was 1.18 atmospheres. And then last for the reaction here, this would be us multiplying by a factor of 1/2. And so then I would take my Kc value, put it to that 1/2 power, and I would find my Kc equals 0.509. All right, so that would be all of that problem. The very last problem here is a challenge problem. I'm actually going to leave this for y'all to do as a practice. So if you would like to check your answer, you can find it on the key. But that is it for rice tables. If y'all have any questions, don't hesitate to reach out and let us know. But otherwise, y'all have a great rest of the day. Bye, y'all.